This is a video about the AQA A-level Chemistry topic of fractional distillation. The good news is that there's very little included in this topic that wasn't already covered in the GCSE, but it is often used as a context for them to ask you further questions about naming alkanes or putting it together with other parts of the organic chemistry specification, so it's definitely worth going over. You first met crude oil during GCSE chemistry. Crude oil is also known as petroleum. Note, that's not the same thing as petrol. Crude oil is an unrefined fossil fuel. It's a finite resource found trapped within rocks, and it was formed from the remains of ancient biomass, as sea creatures like plankton died millions of years ago and their bodies were buried in sediment and slowly broke down. Crude oil is a mixture of compounds called hydrocarbons, mainly of a class called alkanes. Alkane is the name that we give to the saturated hydrocarbons. So hydrocarbons are molecules or compounds that contain hydrogen and carbon atoms only, nothing else. And saturated means that between the carbons of those hydrocarbons, there are only single covalent bonds. Now at GCSE, all you met were these long chain alkanes, and those do exist, but they're not the only alkanes. So in addition to these chain alkanes, we also have branched alkanes that have additional groups coming off them, and we also have cyclical alkanes and even ones based on benzene rings. So depending on the particular properties of those alkanes, they might be more useful as fuels or as feedstocks to make things like solvents, lubricants, detergents and polymers. As you learned at GCSE, fractional distillation can be used to separate a very large mixture of lots of different compounds into fractions. And these are going to be mixtures of compounds that have similar boiling points. And in the case of alkanes, that's going to be because they have a similar chain length. But of course, you can have fractions of things other than alkanes. Now, in terms of the actual process that we're going to go through, we're going to use a fractionating column. And the start of that fractionating column has a furnace, which is heated up to about 350 degrees C. And the crude oil, the unrefined oil, is going to be pumped in through a pipe that passes over that furnace. So watch out here, we're not setting fire to the oil, we're not trying to burn the oil, we're just heating it up. And the reason we're heating it up is that the vast majority of those hydrocarbons, those alkanes, will evaporate. And so they will go up this fractionating column. Now, not all of them will. Some very, very large alkanes are just going to be taken out as liquid, and that's what we call residue. So the remainder of the alkanes which have evaporated are going to carry on moving up this fractionating column. And the important thing about the fractionating column is that it has a temperature gradient. So as we've already said, it's very hot at the bottom, but at the top it might only be about 40 degrees C. As the different alkanes move up this, at any one point in the fractionating column, everything is at the same temperature. So at the very bottom, everything is at 350 degrees, and the only thing that is a liquid is this residue. Then as we rise a little bit higher, the temperature is a little bit lower, so maybe it goes to 300 degrees, and there will be some compounds which between 350 and 300 will turn back into a liquid. So they can be taken off and collected, and they will form a fraction. So as we move up the fractionating column, we're producing not individual compounds, but groups of compounds which have become a liquid at about the same point because they have the same boiling point. So the molecules that are being collected at the very top are the smallest molecules. They have the lowest boiling points. They have low viscosity, so low stickiness. And they're also highly flammable, so they make the very best fuels. We've just said that those very small alkanes, which are found at the top of the fractionating column, are the ones that have the lowest boiling points. But why is this the case? Well, we know that if all other things are equal, if we're looking at the same atoms and we don't have any sort of differences in polarity and things, then larger molecules are always going to have higher boiling points. This is because the molecules are held together by weak intermolecular forces. Now, in this instance, we're not talking about anything that's polar. Carbon and hydrogen have very similar electronegativity, so the bonds between them are not going to be polar. And so the weak intermolecular force that we're interested in is a van der Waals force. And van der Waals forces arise because spontaneously temporary dipoles arise because the electrons are moving around the atoms. And so if a molecule is larger, like my butane molecule here on the right hand side, it has more electrons. And so therefore it's more likely that by random chance at one instant, slightly more than half of the electrons would be on one side of the molecule. And that's going to create a temporary dipole. And that can then induce a dipole in a neighbouring molecule. And then the attraction between those is what's going to create the van der Waals force. So basically, the larger a molecule is and the more electrons it has, the stronger the weak intermolecular forces between the molecules will be. Remember, it's going to be these weak intermolecular forces that are being overcome by the energy. It's not going to be the covalent bonds that are in the middle of the molecule. They are not being touched, they are still intact. It's the weak intermolecular force that is being overcome. That's it for content, so let's go through a few exam questions just to make sure you're happy with what we've covered. First of all, a multiple choice question. Which of these statements is correct? Molecules in petrol are held together by hydrogen bonds. The boiling point of petrol is higher than diesel. Petrol is a mixture of compounds. Or the most flammable product is fuel oil. Well, let's think about this first one first. We know that hydrogen bonds are a type of weak intermolecular force, and it forms between molecules in which hydrogen is covalently bonded to oxygen, fluorine or nitrogen, because those three elements are extremely electronegative. Now here we're thinking about crude oil and petrol, so we're thinking about hydrocarbons, and we definitely don't have any oxygen, fluorine or nitrogen. So immediately we can say that A is not correct. Then B, the boiling point of petrol is higher than diesel. So for this we might need to look back at our fractionating column. Petrol is a mixture of compounds. Well, we know that another name for a mixture of compounds is a fraction. And of course, petrol is one of our fractions. So that is the correct answer. Next, pause the video and write down a definition for the words hydrocarbon and saturated. Hydrocarbons are molecules or compounds that contain hydrogen and carbon only, and saturated means that it only contains single carbon-carbon bonds. Let's do one more multiple choice question. Which of these statements is correct about fractional distillation? Gaseous fractions are formed by breaking covalent bonds. Each fraction contains a mixture of hydrocarbons. The fractionating column is coolest at the bottom, or an ion catalyst is used. Well, I'm going to start off by ruling out D, because we know that there is no catalyst in fractional distillation. It's a physical process, not a chemical reaction. So there's definitely not a catalyst. An ion catalyst would be the Haber process. Next up, I've got the fractionating column is coolest at the bottom. Well, that's not going to be true because the bottom of the fractionating column is where we find our furnace. That's going to be about 350 degrees C. So C is definitely also incorrect. The first option I'm given says that gaseous fractions are formed by breaking covalent bonds, and we know that that's not the case. So we know that those small covalent molecules, when they boil or even when they melt, it's not the covalent bonds that are being broken, it's the weak intermolecular forces. So we can rule out that one as well. And our correct answer is going to be that each fraction contains a mixture of hydrocarbons. Thank you very much for watching, and I hope you found this a useful video in your A-level chemistry studies. If you did find it useful, then don't forget to like and subscribe for more A-level chemistry videos coming soon.